everyone. Thank you for coming. So today we've got two amazing speakers. First, we'll start with Laszlo, who will talk to us about good practices around coding in data science. A big round of applause for Laszlo for the first ever speaker at MLOps Community Bristol. Thank you.
Thank you very much for the kind words, and thank you for the attendees to come to my presentation. I would like to start my presentation with a quote from 18th century Prussian general and military strategist von Clausewitz. Machine learning is the continuation of software engineering by other means. You're going to see in this presentation that we can borrow a lot of ideas from software engineers and apply it to machine learning to make our life easier. The title of my talk is Clean Architecture, how to structure your ML projects to reduce technical debt. First, we are going to see how technical debt ruins your productivity in machine learning, why machine learning products are particularly prone to gather technical debt, and we are going to go through a couple of software engineering principles that can help you to mitigate this, like decoupling, refactoring, or design patterns. About me, I have a background in finance. I was an analyst in mobile gaming. I was head of data science at a London fintech, where we specialize in industrial scale natural language processing for investment banks. Most of the content of this presentation is coming from the experience we gathered during these projects. And please check out my blog, laszlo.substack.com. First of all, it's important to understand of what do we mean by ML products. ML products are not machine learning MLOps infrastructure. MLOps infrastructure is a capability or a feature and a tool what you are using to create ML products. And it is also not data analysis, even as data analysis in advanced analytics uses machine learning technique to solve the problems. Usually data analysis have a beginning and an end. Essentially, when you are providing the insights to the stakeholders, the time period is too short to talk about the product. ML products are complex business processes which are described by end-to-end input-output relationships rather than rules. They work autonomously, so they don't require substantial amount of manual activity and usually has a long lifespan. And that's exactly this long lifespan which makes them removing technical debt a high added value activity, because you are going to have a long period of time when you are yielding from these activities. Why does technical debt matter in ML products? You are solving fuzzy real-world business problems. There is a lot of like edge cases and ad hoc rules of thumbs, what you try to solve, that makes machine learning products inherently unspecifiable. So it means that no matter how much specification you are doing in advance, you are going to find features and aspects of the problem that you haven't thought about even when you are in production. And there is another problem, which is machine learning products and the business problems what you are solving are changing while you are solving them. It means that this is always a catch-up problem. It means that you, by definition, need to prepare that you are going to need to change ML products. Let's take a look at ML Lifecycle and how ML Lifecycle impacts the creation of technical debt in ML products. As we understand now, there is 5 major steps in machine learning. First, you have EDA, which deals with data problems. Then you have a POC, which deals with the modeling problem. The MVP deals with productionization. And the A/B testing deals with fine-tuning, while we think about business as usual as a part of monitoring. What's the problem here if you want to change? Often, this is not even done by the same team. The first 2 steps, EDA and POC, is done by data scientists, who then in turn hand their results to machine learning engineers who deal with this in the other 3 steps. If you try to get a feedback, which is essentially coming to the data scientists that they need to change the product. They first need to analyze how to change the data definition and the POC and hand this knowledge back to the machine learning engineers, who in turn again implement that. And this is what's called a friction, because the communication between these people need to be synchronized. If this communication is slower than instant, it means that there is a chance that you are going to accumulate changes in one go and start handing it over in a package, which soon is going to turn it into a versioning, which is soon going to turn into a business critical problem, because you're trying to create a large change and suddenly you become a waterfall place. Often what we see in our practice, that instead of actually updating a machine learning product, the team just opts to scratch it and write a new one instead of that, which is not a particularly CI/CD solution. What's the difference between technical debt and technical mess? It's important to specify that, because often a lot of things are claimed to be technical debt, which are not actually are. Lack of specification, documentation, and infrastructure is not technical debt. You are just not finished with your work yet. Missing features are just missing features, and broken models, which are particularly prone in machine learning, are just broken model. You need to retrain them or create a new one instead of them. And most importantly, technical debt is not bad practices. You are performing bad practices, that's just reckless behavior. So what is technical debt? Technical debt is an attempt to gain knowledge with a plan to correct it later. It's a very important concept, that it is actually, you're taking a step in an unknown direction with the knowledge of how do you get back to the place where you want to. All right? And I think it is important to stick to the original definition of technical debt, which is corporate debt. So you're essentially investing in something that is going to have a higher yield than the debt itself. If you are thinking of credit card debt, that's an incorrect analogy or metaphor, because buying a new TV is not going to give you too much yield, right? Ward Cunningham, so the person who coined the term technical, said that paying back technical debt depends on writing code clean enough to be refactored. And you can ask what refactoring means. Refactoring means changing the code without changing its behavior. You can think of, why would you change the code without changing its behavior? We know that there are multiple ways to solve every problem in programming. There is no reason that because you implemented it once, that's the best way to solve a problem, right? So refactoring allows you to, once you solve the problem, turn it into something that enables you to solve future problems. And this is exactly the purpose of refactoring. It requires two things. First, it requires fast testing. And the second, it requires what's called experimental operational symmetry, or EOS for short. Let's take a look at this. What is EOS? It's essentially Google's fancy name for running the same code everywhere. Where do you run the same code? You are running it on your laptop when you're writing it. You're writing it, using it on testing, evaluation of your models, training of your models, and then eventually in production. And EOS requires you that these 5 places are running the same code. And we are going to see how to achieve that. EOS enables refactoring, but it also requires decoupling. Let's take a look at what decoupling means. Decoupling is reducing the dependency between components of your system. Why would you do that? It allows you to decompose a problem into smaller pieces, and it allows you to hide implementation details of external peripheria, which is not relevant for your ML products. As you remember, ML products are usually high-level business processes and automations. They should be less concerned about implementation details around databases or external peripheria. And it has the additional value to breaking what's called cake. Changing anything changes everything. This is particularly prone in machine learning. That helps you to detach from that from a software engineering perspective. It doesn't help you from a machine learning or a mathematical perspective, but that's a higher level problem that you can solve in a different place. Let's see how decoupling can be solved in a machine learning situation. Let's imagine that your code is the blue box, defined as a class. And we need to be familiar with two related concepts, which is called inversion of control and dependency injection. In a traditional setting, your program is calling the infrastructure. That's called direct control. You are going through, and then let's say you load a database, then you are delegating your code for training on a GPU, and then you get the results and then do something with it through an API. In an inversion of control, the infrastructure calls the main entry point of your class. It instantiates your product as a class, and then calls the main entry point to do its business. And dependency injection allows your code, which is an abstract Python class, to connect to external peripheria and get the information from it or put the information out there. It is not aware of where is it going. It just understands that it is need to have an interface and connect to this interface. This allows you to create decoupling from these interfaces, but still maintain EOS, because in a test setup, for example, you can imagine that your test harness calls the main entry point of your code, and the injection of the external peripheria through the file system or mock services, where you can see how your code behaves, and does it behave in the correct way. So let's see how to structure the blue box, your code as a product. It's very important that in a clean architecture, your main focus is on the center in a business process that you are trying to implement, which consists of a domain model, which is essentially classes that describe what you are solving. Business logic, essentially extending the business process into your code that is you are implementing, and the models that are automating these problems, right? That is at the center. This has the additional benefits of most of your attention is at the center of this code. You are going to write most of the code here. You're going to do most of the refactoring here while you are testing your code, and it allows you to make this the cleanest part. And this is surrounded by the classic machine learning features like datasets, feature engineering, and other parts. The outer layer, which is treated as an external resource for this product, are the databases, the computing infrastructure, and external services. If you are creating this plugin architecture with dependency injection, that has the benefits of outsourcing these components to other teams, and therefore it helps you to build like a distribution of responsibilities. You can incorporate other people's help into your product in a seamless way. This is what's happening in testing. You can see that the middle of your structure, so the blue box, what you can see on the previous slides, are not changing. You are just replacing the external environment when you are putting it in testing. Obviously, you can create another environment and put it into evaluation, and so on. But the middle, the business logic is the same, no matter where you're running it. We are going to look at 3 useful design patterns that are going to help you in implementing this. Which is called the adapter pattern, which allows you to decouple from external services. The factory pattern that allows you to decouple from data sources. And the strategy pattern that allows you to decouple from algorithmic decisions. Usually you are experimenting with, you would like to try new ideas, but you don't want to destroy your code, and strategy pattern is the best way to solve this problem. So the first one is an adapter pattern. As you can see, it is already refactored our code into a class. The infrastructure on line 17 is played by a shell script, which is instantiating the main class and then calls the main entry point, which is the run function. The run function, in turn, creates an engine connection, a database engine, and then runs a simple query to get a data frame. What's the problem with this? If you take this class and instantiate in your own machine and you don't have access to this database, this code can never run. all right? So it means that you cannot achieve EOS through this because you can't run a test, so you can't do refactoring. So what do you do? Essentially, the simple idea in an adapter pattern is to wrap the code that is dependent on an external resource and move it into its own class, which is here called SQL source. And the main code, you can see that I removed the database specific parts and replaced it with an interface call. From now on, your main code just knows one thing, that it has a source that it needs to call through an interface, and it's going to get a data frame from it. And you can see the infrastructure now instantiates the main code and this database connection. If you want to run it on your own machine, you only need to rewrite that line, place another class which gets the data from a data frame, a file, and move on. Right, so the next one is a factory pattern. Usually, when you are writing your own product, you would like to have all of the code to be domain-specific terminology. For example, if you are dealing with customers, you would like to have a customer class. You don't want to have a data frame which is connecting various bits of data together. Having a domain-specific term is a good idea. And you can see that I refactored here that the source class now returns a list of domain-specific classes that you can use as the native language of the business process and the business problem what you are solving later. So essentially a factory pattern, a factory is just a class that creates other classes, all right? And the last one is a strategy pattern, which is particularly prone in machine learning. Essentially, you can see here that the customer class is turned into some set of features, and that set of features fed to a model, and the model creates a prediction. The problem here is if you would like to try a different model, you need to rewrite this class, which is not great. You can imagine that this is a simple example, but if it's hundreds of lines, you would have a problem of finding where is exactly your model is. So you can wrap all of your problems, and then the same way as you did this with the adapter pattern, you can, as someone said, one of our lectures, you treat the algorithm as an external resource to your code. And you can see that here the model is instantiated in line 19, and the same way it's called a predict function, passed a domain-specific class and get the prediction back, but the main function doesn't know what kind of model it was running. It has another good aspect, which is called coherence, which is essentially, let's imagine that your model is a deep model which requires to decide how many layers it has. These layers need to be passed on to the main class if you don't have this refactored. And this needs to be stored, and this data needs to be passed on to the primary function when the model is instantiated. Obviously, if you would like to replace it, let's say from a deep model into a random forest, which doesn't have layers, it has trees, you need to change your code multiple ways, and the more places you change, the larger the chance that you are going to make a mistake. So what you can do, obviously you can pass the layers to the model if you have refactored it into its own class, and now the main function has no knowledge of the feature, and your code is much cleaner. If you want to write a different type of model, like a tree, then you just need to write a different class and plug it in line 19, and you solve the problem. So what's the workflow from scratch when you are approaching a problem through these paradigms? First, you define your data classes. This is usually part of the analyzing the business process that you want to solve with machine learning and the business logic. Then you wrap any kind of data source with factories that are creating these data classes for you. And then in the future, you operate on this. So set up a test environment. Usually what we do is just run the same pipeline on 1% of the data. This is good enough to pick up if you created typos or any kind of stylistic errors. And the majority of the problem appear to be here. You define your interfaces, any kind of verbs that you want to do with this data, what you want to create these, and then group these into service classes. If you want to move towards a service-oriented architecture or microservices, then this service class is going to be the services eventually. Then you structure these through dependency injections. As you see the coherence before, you create yourself opportunities to enable yourself future experiments. Then you wrap these external services in production that you want to achieve when you move into production with the adapter pattern. And then you can set up a production environment and deploy the same code that you are running in test to production as well. Once it is running and you have new ideas of what you would like to do, you can set these up through the strategy pattern without actually changing the production code. And you can run experiments. Of course, a lot of people works in notebooks. And how do you incorporate this workflow when you are doing your analysis in notebooks? We load the data classes with factories. The factories are classes. You can instantiate them in the notebooks, get the data, turn the data into data frames through dictionaries, and do any kind of analysis and plotting in notebooks. And because your main program is a class, you can instantiate it in your notebook and pretend that you are in production with the right plugins. And you can create experiments through implementing strategy patterns ad hoc in that location. Right? So what's the benefits? We recognize that the biggest benefit here is it has good layers of abstraction. You have a place to do everything. So you have a place to do analysis in notebooks. You write your code in your IDE, your product code, and then you can externalize infrastructure and outsource it to other teams. You have a high level of flexibility. You can do experiments without touching the production code, and you have a large amount of optionality. You have what we call managed complexity. Often you have complex problems that cannot be solved with simpler solutions. You don't want to have simple solutions. What you want is manage the complexity of your existing solution, and this allows you to create difficult solutions or complex solutions and still maintain coherence and consistency and your sanity. And lastly, it allows you to have high-speed iteration because your code is running on your laptop and in test environment and in evaluation. You can change it, and then you can, if you can run it a test and it passes the test, you can immediately push it into production. And this is coming from EOS. Takeaway. So we see that ML is inherently unspecifiable. Tech debt is inevitable. Only refactoring can remove technical debt. No refactoring without testing and EOS. And EOS needs decoupling. Decouple through clean architecture, that's one way to solve that. And you can use IOC, so inversion of control and dependency injection to solve that. And 3 simple patterns, adapter and factory and strategy, are the ones that you only need to learn. Obviously, there are other ones as well, but this is a 30-minute presentation, so I try to go through as many content as possible. And please check out my blog on laszlo.substack.com. And thank you for your attention, and we can go to questions.